Hi everyone. So I want to do a little bit more about mathematical induction. I know it's the last lecture, but there will be a question on the final about mathematical induction, but we cannot do a quiz anymore. We don't have the time for a quiz. So, but what I'm going to do today is a little bit more advanced mathematical induction. So in some sense, it's less something that the type of questions that I will solve, prove here using mathematical induction are not the ones that you will get on the final. It's more like what the homework problems were like, and the one that I did in the previous lecture. But it is good to see how mathematical induction can be used in many situations, and just see it at work. That at least if you see it in a bit more, if you understand how it works in this more, let's say, advanced problems, then you also can more see, then you can also figure out how it works in the in the simpler cases. So let's start with, so far we have been proving equalities or inequalities. So here's another one statement is that for all n, so again, but we don't write this, so whenever we say a statement like this, that n cubed minus n is divisible by 3. That's the statement. And of course, again, there's no universal quantifier. That means actually, we claiming actually this is for all n. And therefore, so the proof by induction, what we do is 2 steps always. The basic step, and that is always, not always, be careful. Sometimes it's actually the hardest, but in most cases, probably every single case that you run into, this will be the simplest case. So what is the basic step here? We have to actually kind of define here where we start. And we can start here at 0, we can start at 1. There's no stipulation, there's no restriction that n should not be 0, so let's start from 0. So this is n equals 0. In other words, the statement P0. So what is the statement P0? So I'll write a bit, so I'll put quotes here to write the statement out in case n is 0. So it just means in that quoted sentence, I just place the n by 0. So 0 cubed minus 0 is divisible by 3. Now this is actually, the previous one was actually a predicate involving n, but this one is an actual statement about a proposition. So it's either true or false, and it is clearly it's true. So this is true. Okay, and that is the basic step. Now the induction step, and this is where we have to set up first. So for the setup, there are 2 parts. We assume that Pn is true, and to show that also the next one, Pn plus 1, is true. Okay, remember I would highlight these by saying this is a true statement, and this is orange. We don't know yet whether it's true or not. Okay, so it is always good to write out what do we have. So we can assume that n cubed minus n is divisible by 3. So that is, so we know that this is true. Okay, what do we need to show? So let's start here. Now there's no left and right hand side, there is only this expression. But what is this expression in terms of n plus 1? So okay, let's perhaps say, what is n plus 1 claim? N plus 1 says that n plus 1 cubed minus n plus 1 is divisible by 3. That's what Pn plus 1 says, and this is what Pn says. Perhaps I should put it there. Okay, so this is the statement that I know here. I'll make this also green. So this is the thing that I need to prove, and this is the thing that I know. Okay. So what we have to, since we don't not have left hand side, but we still have an expression. That's very often you have some expression that you start manipulating, and the expression that we have is this expression. Not this one, because we know the truth about this. We start from the thing that we don't know, and hopefully we can rewrite it in a way that we can see what is happening with it. Okay, so in other words, I'm gonna go. So I'm not doing this part here. Let's go straight to this one here. So n, I'll write it here. N plus 1 cubed minus n plus 1. Well, it clearly can be expanded. So let's expand this. Now, you can FOIL this. This is the first one that we have to expand, right? Be careful. It's not n cubed plus 1. I hope. So a common mistake would be here, so I'll do this in red. Say, oh, this is n cubed plus 1, and then minus n plus 1, minus n minus 1. So these cancel, and this is the same as n cubed minus n. We know it's divisible by 3, so this is divisible by 3. Wrong proof, because it's wrong algebra. We used induction correctly, but we used the wrong algebra. So that's a mistake that we can also make, because the cube of two numbers is not just the cube of the numbers. That's absolutely not true. So what is it then? Well, there is the so-called binomial formula, but you can also FOIL it out. If you don't know the formula anymore, work it out, and n plus 1 times n plus 1 times n plus 1, and you see this becomes this. This is the expression for that. So let me erase this wrong thing here. So what I'm claiming is that, I'll do it in different color here, that this expression is the same as this expression. Okay, and then we have to subtract n plus 1, but of course we have to distribute the minus sign, so the result would be this. Yes, okay. And now comes a little bit of trick, and this is perhaps the hardest part of all, is that you have to fight your inclination to say, oh, okay, these are like terms, so I take them together. Now, and these are like terms, so they cancel out. Now, the second one is correct. I should do this. But I don't want to combine these. Why not? Well, I always have to keep an eye on the price, so to speak, or an eye on this green guy here. I have to find somewhere in the expressions that I get, I want to recognize the previous expression, which is n cubed minus n. Now, it is there. This is n cubed minus 1. Minus n, sorry, I said n cubed minus n. Right, I misspoke here. N cubed minus n. That is what I'm on the lookout for. I see it, and I don't want to destroy it. So that's what I'm going to do now. I'm going to say that is n cubed minus n. So I take these two together, and then the ones cancel. That I don't want. But then I have a 3n squared and a 3n. Now, why don't I mess with these? Because remember, it's all about divisibility by 3, and this number is clearly divisible by 3. It's a multiple of 3. This is clearly divisible by 3. And what about this one? It's divisible by 3. We just say this. So by our induction hypothesis, remember we write this induction hypothesis, this is divisible by 3. So we have 3 numbers divisible by 3, and we add them up, it's still divisible by 3. So the conclusion is that this thing is therefore divisible by 3, and that's the only thing we need to do. So it's actually very short, but you have to combine you have to match somehow the previous situation. You have to manipulate so that it matches the previous situation. That is a little bit novel way of working with these things. Now, incidentally, this proves, remember we saw the Fermat's-Little theorem. Let's remind us what Fermat's-Little theorem says. For the prime p is 3, that it says that a to the power p minus 1 is equivalent to 1 mod p, which is, right? This is the general statement. So for p is 3, this becomes a squared is equivalent to 1 mod 3. Let's prove this. Well, this was for a not divisible by p. So this is true for a not divisible by 3. Okay. So what we just proved, we didn't prove this yet. Remember, the statement was slightly different. The statement was that we now proved. Let's write it again, what we now proved, but instead of writing an n, I use an a. A cube is equivalent to a mod 3. That is what we proved, right? This is divisible by 3 is just a more cumbersome way of saying this, much more compacting if you use modulo notation, right? So it is actually better to say a cube is equivalent to a mod 3. That exactly means that a cube minus a, the difference is divisible by 3. Because what does this mean? Remember, this means that this number, if you divide by 3, then the remainder is the same as doing this for this number. So if you subtract the two numbers, what you're saying is that the remainders cancel, and therefore this whole number becomes divisible by 3. Look up back what this mod means, because it's important that you understand how this is the same thing. Now we have an extra condition here, right? Because we know this is not true if A is divisible by 3. If, for instance, if A is 3, this is 9 is not equivalent to 1 mod 3, because 9 is 0 mod 3, right? So we have to use this. Now, when something is not divisible by the prime p, then it's invertible. Then it has a multiplicative inverse. So we know that there is a b, so that b is equivalent to 1 mod 3. Remember, if the GCD of a number is, the GCD is 1, then that number has an inverse modulo the other number. This is where we use this here. Okay? Well, let's now multiply this equation with this. We know there's such a b. There is a b. There is, actually there's a unique b. There is b such that is using the multiplicative inverse. Now, if we know the a, we know how to calculate it. Remember this by the division algorithm and the Euclidean division. So, but let's not do that. We don't need that. We only need that to know that it exists. Because now multiply both sides with b. Well, I get a cubed b is equivalent to a b mod 3. We know that doesn't change if you multiply both sides. Now, this becomes 1. What happens here? Well, this I can write as a squared times ab, and then this is 1. So this is the same as a squared. See, a squared is equivalent, I'll go around here, so cut through. A squared is equivalent to 1 mod 3. And that is Fermat's little theorem that we proved. And that is, by the way, how you prove it. We proved this here for 3, but this is true for any prime. N to the p minus n is divisible by p. And the proof is exactly the same, except that you need to know then this is the binomial theorem for cubes, which people tend to memorize. But for higher p, it gets a more complicated formula, and then you have to analyze that formula a little bit. But that's not the part of what I want to talk about now. Okay, so another one, a bit harder to work with, so it needs a little, it's less straightforward in that you need to do a little clever thing. And so this is the one here, is that, 7n plus 2 plus 8 2n plus 1 is divisible by 57. That's the claim. Okay, so this is again the statement, Pn. So let's do this. And since they don't tell us for which ends, we assume that the basic step here is 0. Proved by induction. Don't wait for the whole movie to finish. If you think you know what to do, try it out and then check whether I did it, whether it comes out the same as what I'm doing. So the basic step, I mean to say, pause the movie and then try it and then look at it, okay? P0, what does that say? That is 7 to the power 0 plus 2 plus 8 to the power 0 plus 1 is divisible by 57. That's the statement. Question, is that true? Well, that is 49 plus 8. Well, that is 57. So yes, of course, that is divisible by 57. So yes, P0 is true. You see that P0 here is not immediately obvious. We do have to do some little calculation here. Now the induction step. Pn. Oh, sorry, yes. So induction step, Pn. No, sorry, let me write it this way. So in the induction step, there are two things. We assume Pn, and we show Pn plus 1. That's the task that we have to do. So Pn is a statement. I'll write it up one more time. 7n plus 2 plus 8 2n plus 1 is divisible by 57. It's important. It's good practice to write this out now for n plus 1. That means in this expression I replace n by n plus 1. It's clear what the new exponent of 7 becomes is n plus 1 plus 2, n plus 3. Now be careful, here we have 2 times. So this exponent here, write it here, is 2 times n plus 1 plus 1. Right? It's the n that I replaced by n plus 1. So the 2 is in front of all this. So this will come out to be 2n plus 3, right? 2n plus 2 plus 1. Okay, 2n plus 3, everybody sees this? 2n plus 3. 2n plus 3, and that is divisible by 57. Okay. So somehow I have to, so let me mark it again a little bit that we get clear. It helps if you color things a little bit that you know what the status of these statements are. The green one is something I can use all the time. The orange one is something that I'm in the midst of proving. Okay, so and therefore I'm going to look at this expression again. 7 n plus 3 plus 8 2n plus 3. And now I want to mimic somehow this forms. Okay, so here's an n plus 3, I need an n plus 2. How can I do this? By factoring out one of the 7s. Right? So this is the same as 7 times 7 n plus 2. Because multiplying is adding exponents. We normally do it in the combined way, but now we decombine it, so to speak. Right? What do? I want to also get this form here, 2n plus 1, but I have a 2n plus 3. So how much powers of 8 should I factor out to get the same result? 2 powers, right? 8 squared times 8 2n plus 1 now. So this is now correct, okay? I mean, it's easier to see from right to left. It's a bit harder to think of it from left to right, so to speak. Okay. Now the problem is, well, let's write out what a square is. I could have done this, but let's do it here. Is 64 times a 2n plus 1. Okay. It's not okay. I have now each of these individually. I have this one and I have this one, but that's not really what I want. I need a sum of these. So there's this one plus this one, but there's a 64. They're different coefficients. They're not like terms. Okay, so I would like to have some like terms. How can I do that? And again, this is something that we are deconstructing, desimplifying instead of simplifying. I'm thinking of, what if I break 64 down here into a 7 and whatever remains? Because then at least I have the common 7 here, and then I can perhaps factor out that. So I'm going to do that. So what I'm going to do is I'm going to split 64 in 7 plus, and what's the rest? 57 times 8 2n plus 1. Okay, why do I do this? Because then I have 7, I'll write it out. I take my time to write it out so that you see where everything comes from, because otherwise you say, what is this magic you're doing here? There's no magic, it's just basic algebra. It's just a bit weird. It's kind of, it's like, the normal game is we have all these Lego blocks and we put them together and we make a nice little building. And now we're doing the opposite, we're breaking it down. But what we now have is here 7 times something plus 7 times something, so we can factor out the 7. So we get this. And why am I interested so much in this part? Because that's exactly this expression here. So this is exactly, I now got this expression. Did this help me? Well, what do I know about this expression is that it is divisible by 57. So this thing is now divisible by 57, but it is magic, right? This is 57 here as a factor, so this is also divisible by 57. Let me copy that here. And that is the secret of the solution, of course. I hope that you see it by now. So by the induction hypothesis, this is divisible by 57. So we have a term that is divisible by 57, and the other term is divisible by 57. This is divisible by 57 by induction. We don't know exactly how it factors, but here we see the explicit factoring, and so it's even much clearer. This is divisible by 57, and therefore the whole thing is divisible by 57. So this is divisible. Well, I shouldn't perhaps divisible by 57, and that is what we want to do. Okay. Another one, to show you that it doesn't all have to be numerical problems, and I'll do 3 more, I think. Let's prove that the number of subsets of a set with n elements is 2 to the power n. So what I'm saying is if you have a set with n elements, then the number of subsets, all possible subsets, is 2 to the n. Okay? So part of this is, of course, the basic. Sometimes you might think this is, you want to understand really what this set says before you even attack it. So you might say, what happens is, so we want to try out for small values for n. So let's say n is 2. So this is, I'm not doing the proof yet. So understanding, so this is understanding the problem. This is something you should consider doing. This is, but people sometimes forget that this is actually part of the process. It's not something that you're going to get any credit for. I mean, unless you, well, you could write it down, and if you cannot do anything else, at least write that down. I'm probably going to be generous and give you some extra credit. So understanding the problem means what is checking that this makes sense, what is said here, to figure out what is said and does it work for these small values and for small values. It is not a proof. It is part of the thought process, but not the part that actually gives the formal mathematical proof. The other one is somehow convincing evidence. It's in court it might hold up, but not in mathematics. Okay? So let's look at this, what this would be. So we have a set of two elements, A and B. What are the subsets? So this is the set. What are the subsets? Well, we can take one of the elements. We can take the other elements. Remember, a set with one element is sometimes called a singleton. Are there other subsets? Yeah, of course. The whole thing is always a subset. Yeah. Well, now let's see what the number should be. Here n is 2. This should be what? 2 to the power 2. This should be 4. Oy, I have only 3 subsets. What am I missing? You see what I'm missing? The empty subset. The empty set is always a subset, right? So we have the empty subset, we have the 2 singletons, and we have the whole set, and that's it. So there are 4. So yeah, it works out with n is 2. Perhaps that might be luck. We might have luck. So it doesn't prove it at all. And even if we do for 3 and 4, 5, and 6, it starts more and more getting we start more and more get convinced that it might be true, but it might be a freak of nature, and we don't know. Okay, so here's the proof. So proof by induction. But again, don't worry. These proofs are a little bit trickier. So what I'm trying to say is, I do not expect you to come up with this proof, but I do expect you to understand the proof once you see it. That's 2 different processes, right? Okay. So any proof with induction has a basic step. So what can we take here? You can say, oh, the size of a set, the number of elements has to be at least 1. But then you think, no, it actually doesn't. I can do n equals 0. So what is P0? Well, what is the set then? So let's give the number of subsets of a set S. Let's call the set S. So S, so this was S, right? So what is S then? Well, S is the empty set. That's if n is 0 and S is the empty set. Now, what are the subsets of the empty set? Well, the empty set, we know that's a subset. So here are the subsets. And the set itself. But that's, again, the empty subset. There is only one subset, this empty set. It is a bit, somehow, feels a little bit counterintuitive. You have nothing and it still has a subset. Well, yeah, because we consider nothing to be a subset, always. So this nothing is a subset of nothing, right? So, right, so this tells me that the number, that we're going to have to give a name here to this, the number of subsets of a set S with n elements is 2n. Okay, so the number of subsets, I'll write just that. I hope that is clear. The number of subsets is 1, which is 2 to the power 0, which is exactly the formula. So that works out. So now the induction step. Okay, so assume Pn. So that is saying that if you have if the set has n elements, then the number of subsets of S is 2 to the power n. I'm going to make it write it cryptically down like that, but I hope it is clear what it says, right? So this is what we assume, and then to show that is Pn plus 1. I don't know why my E got separated from the rest. He was not paying attention. Okay, yeah. Pn plus 1 says that if the set has n plus 1 elements, then the number of subsets of S is 2n plus 1. Now you might say, Professor, but shouldn't we use a different letter here, because S is a set with n elements in the first one and the second one is a different, so it should be different. Yeah, okay, I agree with you. Sometimes mathematicians say, okay, when I assume something that is this one, and then this is it's a variable that I use in a different context, but perhaps it is helpful if we write this as a different set. Call this just the different set, a set of set T, and let's call it that way. Okay, I agree with you. Okay, so proof. Okay, again, this is what we need to show, and this is what we know. I'm going to start again with T. So I'm going to start with T, and let's make a little Venn diagram. Okay, this is T, looks like this. Well, I didn't fill in anything yet, but here comes now the clever trick. So this is the proof, right? The proof, the actual argument. And this is, again, don't worry about this. We are now in this, I'm now giving you a proof that is a little bit more advanced, but I hope you still understand it, and that this is induction. There is one thing I did not yet really emphasize here, is that in the induction step, we take n to be bigger than the initial one. So far this was not really an issue, but now it is a little bit important. So when we do a proof by induction, we can assume already that n is bigger than the first step, because we already proved the first step. Why bother, right? Okay. Well, actually, that's not even true. Let me not say it. It is, what I'm saying is correct, but we don't even need that here. Sorry. Okay. Let me not confuse you with this. So what we know about T is that T has n plus 1 elements. Okay, and n could be 5, 100, a billion. It could also be 0, actually. But it means that T has at least one element. That's clear, right? It has to have at least one element. So pick an element of T. Pick your favorite element of T. It has at least one. Pick one. Okay? So, can I finally fill in my Venn diagram? That is A. Okay. So, now I'm going to take, let S, not X, let another letter, let V be a subset of T. Okay. So V is some set of T. Now there are two possibilities. Before I draw the V, there are two possibilities. So either A lies in V or A does not lie in V. Correct, right? It's either that or that. So let's look at the first. Let's do this in two different colors that you can see the two different effects. So I'll do this no, I don't want to use any of these colors. I want to use blue here. So A lies in V. So if I draw this, this is where V lies. Okay. And the other is, let's do this in purple, that A does not lie in V. So this would be V. And the blue and the orange have not. Okay, there are two different locations, right? There are two different sets. Now, let's work with the simplest one first. Namely, that's the purple one. So allow me to do this. What I'm going to do is I'm going to look at the purple one first. So this is V, as I said. So V is here. It doesn't contain A. So what does this mean, actually? That V, what does this mean? That V is a subset of T where I remove A. Remember this? Oh no, right. In the textbook we use this notation, right? T minus A. So T minus A is everything in T that is not A. And V is, you see it here, right? V is a subset of that. Okay? So if you take an arbitrary subset of T, there are two types. And they're different types. And so what I'm going to count how many of these types there are and how many of these types there are, and then add the two together. That's all how many there are going to be in total. That's the process I'm going to do. Okay? So I repeat. I want to count, what I need to count is the number of subsets of T. I take one such subset and I divide this class, the subsets of T in two classes, two different classes. They have nothing, they are completely separate. They are disjoint. And then we can use the formula for the sum, the number of elements in two disjoint. The union of two disjoint sets is the sum of the first plus the sum of the second, because they have nothing in common. That is the exclusion-inclusion principle that we can use here. For disjoint set, it's much simpler. It's just adding. So we look at the number of sets of this type. Well, such a set is actually a subset of this set. Now, how many elements does this set have? If I calculate the number of elements, well, the original set has n plus 1, I removed 1, so this is n elements. My induction hypothesis says there are, how many possible v's are there? Exactly 2 to the n, right? This is now the subsets of S. What is S here? This is now my S. And V is a subset of that, right? I said V is a subset of this guy, so V is a subset of this guy. So, and that's a guy that has n elements. Therefore, there are 2n of them. The induction hypothesis, there are 2n of these purple V's. Let me write it simply like that. There are 2n of the purple V's. What about the blue V's? Okay, so let's now draw a blue V. Okay, blue V. So how does a blue V look like? A blue V must look like that, right? Let's look there. Now let's look at the following. Let's look at V minus A. Because A is in there, so I can remove it. Okay? What do I get then? I get a subset, let's write it with the subset notation, of T minus A. Right? If I remove V lies in T and A lies in, so we have A lies in V and V lies in T. If I remove A, then V minus A lies in T minus A. Correct. Okay? So, now any subset, I'm claiming that if I look at all possible sets of this form, I'm going to get all the subsets of T minus A. Because if you have a subset of T minus A, so how does a subset of T minus A look like? So that would be a subset here, right? How do I make, what I'm going to do now is if I add A to it, so this is this subset, union A, that would now be one of the blue V's, right? I take an arbitrary subset of T minus A. In other words, it doesn't contain A. Now I add A to it, and therefore it becomes a subset of this form, okay? And vice versa, if I start with a V that contains A and I remove A, then I get a subset of this form. Then this is the red guy that I had. So my claim is that if I look at the subset containing V, if I want to count them, there are exactly as many as there are subsets V minus A that contained in T minus A. Now, how many are there in T minus A? And I can repeat the same argument. I know exactly how many there are, namely 2n. So the red ones, every red subset, okay, every red subset is going to be a subset. If I can make it into a subset containing VA by adding it, okay? And I'm removing it again, I get the original subset. So we have the same number of red subsets and blue subsets minus A. So every red subset is a subset of this form, and every subset of this form is a red subset. Okay, so they have the same number, and we know by induction hypothesis again, by induction hypothesis, there are 2 to the n of these blue V's, therefore. That's the induction hypothesis, that's the same thing. You might say, but Professor, but this one is one of those purple ones. We counted them. Yeah, you're right. We counted those. But look, that's not what I'm counting. V is not a red subset. V is a red subset together with A. And those we didn't count yet. because these were exactly the ones not A. Okay? So here I'm counting the ones that do not, the ones that have nothing to do with A, right? Those are subsets of T, and these are the subsets of T, nothing. Here I'm counting subsets of T that contain A, but I kind of don't see A. I pretend A is not there, and then all of a sudden they become subsets of T minus A, right? And exactly every subset of T minus A can be made in such a thing by, how do you do that? Well, take a subset of V minus A and add A to it. Now you have a subset that contains A, and that's the same amount. So altogether, so what we have now we can hear the number of subsets of T. Well, there are these guys, there are 2 to the n, and there are these guys, that is also 2 to the n, and we said it's adding because they have nothing in common. There's no term to subtract here, but that is 2 times 2 to the n, which is 2 to the n plus 1. And that is exactly what we needed to prove. Okay, this is already a little bit harder to see here, and you have to think a little bit about it. We split here the problem in 2 parts, and we have to argue on each part separately. I'm going to skip a couple of things that are in the textbook. I want to go to a bit more fun games somehow. Okay, so this is the odd pi phi. Odd pi fights. Okay, this is a game that we play. So what do we have? We have a number of people standing in the yard. So there's a number of people here. I put here one guy, here one guy. Let me put one guy here and one guy here. And the one assumption that we make is that they are all at different distances from each other. Okay? If you just stand randomly, this is going to happen, right? To have the same distances, you kind of have to start standing orderly, right? So 1, 2, 3, 4, 5, 6, 7, 8. I need one more. I'm going to put one guy here. So they are all different distances. And so what you do, everybody has one pie in his hands, freshly baked pie. This is from the slapstick movies, the black and white movies. I don't know if you ever saw these things, where what you do in these movies, when there's a pie, inevitably everybody, when you watch these movies in the old days, people start giggling when you saw a pie, because you know the pie is going to be thrown in somebody's face. Okay, it's just a tension, which face is going to throw in. And so that is what. So what you do is throw pie to nearest neighbor. That's the only thing you need to do, to the nearest neighbor. And since we're saying they're all at different distances, and I'm not writing that down, means that it's always clear what your nearest neighbor is. It's not that they're 2 at the same distance and then you say, which one should I throw to? No, it's clear at any time which one is closest to you. Okay? So that nearest neighbor is going to get a pie in his face. Now you say, oh, so what happens is I see. So they pair off, and this guy throws a pear to the other guy, throws it back. No. That's not exactly what happens. Look at this guy here. This guy, who's he going to throw to? This is his nearest neighbor. But this guy is not going to throw back at him. He's going to go through this guy because that's his nearest neighbor. So it is not so that they each throw pies at each other. Okay? So now the claim is, if there is an odd number, of people, an odd, then one is pie free, meaning he doesn't get a pie in his face. Okay, that's what I'll write it that way. Doesn't get a pie in his face. First of all, this is not true if they're even number, because, for instance, here, this is an example of there are 4 of here, and this guy is throwing a pie here, this guy is going to throw back, because they are both each other's neighbors, and the same here. Okay? So, everybody gets a pie in his face. So, an odd, if you're dealing with an odd one, it is not true. If you're dealing with an even number of people, this is not true. Here is an example. Okay? Well, you could say, oh, but just because you're at the same distance. Sorry, I should have drawn it perhaps this way. So no 2 are at the same distance. or let me put it even if you might still think, oh, but that's the same distance. So I hope this will convince you now. Here, this. Nobody is at this, no two, all distances between the two people are different, but still, the nearest neighbor for this guy is this, and the nearest neighbor for this guy is that guy. So they throw at each other. Now, you see, if there would be a fifth person, he would throw at somebody else. So there you can see what the difference between odd and even already plays a thing. Okay, so we want to prove this now by induction. Okay, so this is a statement. An odd number n. Now, instead of, how does an odd number look like? We know that an odd number looks like 2n plus 1. So I'm already going to make it in this way. The first odd number is 1, the second odd number is 3, then 5. So n counts here, n is not the odd number, n is the how many odd number are you talking about, right? So just if n is 1, then if n is 0, then we get 1. If n is 1, then we get 3. If n is 2, we get 5, and so on. This is 2n plus 1. So my counter n goes from 0, 1, 2, 3, because induction always has to be on a counter that goes with steps of 1. But my quantity here, 2n plus 1, goes by 2, right? It only skips the even numbers. Okay, so this is my statement Pn. Well, let's look at the statement, oh, I see. The statement P0 is already false because there is only one person, yeah? So I'm going to have to add something here. So P0 is false because then P0 there's only one person and it has nobody to throw to. Well, you're not supposed to be throwing to yourself, by the way, right? To the nearest neighbor, not to yourself. You're never considered a neighbor of yourself, okay? So with one person it's actually not true. So P0 is actually false. But that's why I meant the statement. It's not P0 is the case 1, but I want to start from case 3. In other words, I want to start the basis step here is at 1 and not at 0. So here you see where the basic step does matter. So the basic step is for n equals 1, that is P1, and P1 says 3 people. So let's look at the 3 people. Oh, they stand therefore in a triangle, right? No, that should. What I'm not trying to do, what I'm trying to do, it didn't do. The only thing it doesn't have to be is it cannot be an equal. Okay, these are now 3 different triangles. So let's see. When you have 3 people, they're always going to be if there are always 2 that's going to be closest to each other, right? There's always a third one that is further from the other 2, right? That is just triangle observation, right? There's one side that is the smallest side. There's a triangle, and by assumption, the 3 sides are different. That's what we're saying. The distances are different. So the 3 sides of this triangle, okay, so let me draw the triangle, are 3 different sizes. And there is one smallest size, and those smallest size, these 2 guys will throw pies to each other. Okay? What is happening with the third guy? Well, he's going to throw to the one who is nearest to him, but nobody is throwing at him. So he will be pie free. So some guy gets 2 pies, namely this guy will get 2 pies, right? Because in this case, he's the closest by. But that's not, we're not talking about that. We are talking about somebody who's not getting a pie. So for 3, it is correct. So now the induction step. So assume, okay, now I'm not going to spell out anymore what it is, for 2n plus 1 people to show for, but I do need to figure out what is the number here. 2n plus 2 times n plus 1 plus 1. That's the next one. This is Pn, and this is Pn plus 1. Okay, that is 2n plus 3. Okay, so we have 2n plus 3 people. Okay. So here is our configuration. Let's go back to the configuration. And so now I'm going to do the proof, but I'm going to do the proof a little bit on the picture. I'm not going to spell everything out. As I said, this is more for you to understand than to actually figure out yourself. So let's do it on the picture here. Let's give names to at least 2 people. I'm going to, out of this odd number, this in this case there are 9 here, but we should not use the exact quantity of people here, right? Is this 9? Just going 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't forget this one here. I'm going to pick the 2 people that are nearest to each other. Okay? Okay, let's look at the 2 people that we have here. Which are these? So I'm picking, so pick the closest pair. So this is A and this is B. A and B. I call them A and B. Alice and Bob. Okay, here are Alice and Bob again. Instead of exchanging secure keys, they are not just throwing pie at each other. Since they are the closest pair, let's be clear on this, they're going to throw at each other, right? There's nobody closer to A because the closest distance is AB, between A and B. So Alice throws a pie. Here's my pie, she says, and Bob throws a pie back at Alice. Okay. Now, I'm gonna erase this a little bit here. Keep in mind what we have to say. I hope you have a long enough short-term memory to remember the statement, right? If it's necessary, I'll write it up again. I need some space here. Okay. Again, I'm going to have these 2 cases to consider. Let's deal with the easiest case first. The easiest case is, and this picture is not in that situation, but I'll write it down. So case 1, no one else throws at Alice and Bob. Now, as I said, this is not the case here because this guy, the nearest one is B, so he has to throw to Bob. So we're going to have to, for this particular case, I'm going to have to move this fellow here. So I'll do this. I'm going to move him here. So now he has closer neighbors. So he's not going to, nobody, if you look at it, all these people that are somehow close to these 2 guys are still, they have other people closer to them. So they're never going to, none of them are going to throw, yeah, you might say, Professor, this looks like these 2 have the same distance here, so perhaps I'll move it a little bit down here, okay? It's hard to look, let's say, if you measure up to the millimeter, they're all different, that's for sure, because it's almost impossible to draw equal distances here. Okay, so this is the first case, okay? Now, let's consider, therefore, the group of people here, this group of people, this bunch. What we just said is that they're throwing pies at each other because none of them is throwing pies at these guys. Oh, so we are in the situation of we can ignore Alice and Bob. You say Alice and Bob, they are always hanging out together. They are like these, like they like to do their thing on their own. They never want to play with the rest. So let's ignore Alice and B and let's play, guys. Okay, how many people are we here? How many people are there in the green size? The number of people here. Well, remember the whole number of people. So this, how many people were in total? Sorry, I should have put it here. So the number of people here. Remember, we are proving this here. So we are showing this 2n plus 3, right? And we know it's true for 2n plus 1. Just want to emphasize that. So what we are doing here is we are proving this, right? So this is the number of people is 2n plus 3. Now, how many is sitting in the green part? Well, it's the whole group minus these 2, Alice and Bob. So 2n plus 1. Oh, but if there's 2n plus 1, I know that it is true In other words, one of these guys is not going to get a pie in his face. End of story. Okay, that's good. So if that's the case, we are good. But what in the original case? So let me go back to the other situation. So that's case 1. I'm going to erase this case now. Let's look at the case that I originally had. So I'll move my guy here closer to the pair A and B. So this guy says, no, you guys, Alice and Bob, this is Eve. You know, see, Eve is getting, what happened? Okay, I'll write E here. Eve says, I want to hear what A and B are doing. So she gets a bit closer to them, but not too close. They're still throwing pies at each other. But Eve, so let's call her Eve, right? She now throws a pie to whom? To B, right? She throws a pie here. Okay. Okay. How many people are now left here? Let's count these people, this group. How many are there? 2n, right? The size of this set is 2n. Is it okay if I write it this way? Why? Because there are 3 people here. And in total there are 2n plus 3. So this consists of 2n people. Okay. So there are 2n pies at yes, yeah, right, that. Okay. Each of these 2n people each still have to throw a pie. These 3 people have thrown their pie. So how many pies are still flying in the air, so to speak, without us knowing where they land? 2n of them. But now I'm looking at a different set, and this is perhaps something that is strange. Let's now look at, let me perhaps make it green again. Let's look at this set. How many people are in there? So 2n plus 1 people are in there, right? Because now I put Eve back in there. Okay, now let's think. The green, there are 2n plus 1 people. But we just said there are only 2n plus 2n pies being thrown. Right? These 2n people in the black circle here, they have to still throw a pie. They still are measuring who's closest to me, who should I throw to. Right? So 2n pies have to still be thrown, but at whom? If you look at these green people, because it is very well possible that somebody has to throw a pie at E here. For instance, okay, I have to move things a little bit again, but suppose that this guy is somewhere. Oh, no. I move this guy here, say. Somebody is going to throw at E now. This guy has to throw at E because he has nobody else close enough. Okay? So it's not that E is safe at all, just because he's standing too close to Alice and Bob. No, that doesn't make you safe. So in this case, this guy will throw at Eve. So we have to consider this whole, everybody except for Alice and Bob again, the same guys as the previous argument. But what is the difference now is, okay, this guy might throw it here, and this guy probably throws there, and this guy might be throw there, this we don't know exactly by pictures, a little bit unclear. But the whole point is 2n pies, and how many people? 2n plus 1 people. Look, I know big rocket science, but I think this is not rocket science, right? If there are 2n plus 1 people and only 2n pies, one guy is not going to get a pie in his face. Who that is, we don't know, but we know for sure there is one. So also in this case, because there are less pies than people, we are done again. Okay, that's a proof. Again, you have to, the difficulty here is to convince yourself that I actually proved this. Okay? And for instance, what you could do is like look at an example, let's say of 5 or 7, and let the proof be at work. And convince yourself that it works. Of course, you can just figure out who is thrown to whom, but if you follow the steps of the proof, it works slightly different. I'm not going to do that. I'll do that in the next one. It's a bit more clear what I mean here. And that's the last one I'm going to do. So we're going to use something called a triomino. What the hell is a triomino? Everybody knows what a domino is? A A domino is a piece that has two, it's like a rectangle piece with two parts. And it normally has some numbers here and some numbers there. But we are not gonna, we don't care what is written here, we just, it's the shape. For us, it's only the shape. So what is a triomino? Well, that is this shape. That is now something with 3. So this looks like that. Sorry, this is not a good line. So this is a trinomial, but this is not, but the shape will matter and also the orientation of the shape. So this is one, but we could also have this one, right? The one where we have this one, that's another one. And then we could have this one. And then finally we could have this one. Okay, so there are 4 types of trionimos. Okay, and it is, we're going to make distinction between the 4. So this is a triomino. Okay, it's just a name somebody invented for this particular game or games like this. And now we have a chessboard. So this is chessboard like this. Now, the regular chessboard, I hope everybody knows, is an 8x8 chessboard. But here we have a 2n×2n chessboard. So the size is always a power of 2. So we would have what are the possibilities? Well, if n is 0, we get a 1x1 chessboard. So we're going to not do this. We're going to assume that n is at least 1. Okay. What is that then? A 2x2 chessboard? That would be something like that, right? That's a 2x2. What would be n2? If n is 2, so this is n is 1. If n is 2, we get a 4x4. That would be look like this, right? Okay? All right, so clear what we mean and so on. And so we have a 2n×2n, but we're going to take out one of the squares. Okay, or whatever, or we cover up, let's put it this way. I'm going to cover up one of the squares. I'm going to make one square covered up. I use blue here. So one of the squares, oh, that's too big. I need something smaller. One of the squares, randomly chosen. So let's say this square, I'm making blue. Okay, and the goal is now, we have now these trionimos, which I also think of as blue pieces. The question is, the statement is that you can cover the rest with trionimos. First of all, why do we have to cover one? Well, let's even look at the very first case here, which is, by the way, our basic case, but let's just do. If I do not cover one of these, there's no way that the trionimos are going to cover. Well, when I say cover, I mean without overlap, right? Of course, I can put one here and one there, and then they cover, but then there are overlap. So I want to fit these pieces like a puzzle, right? Think of these as puzzle pieces, and you have to fit in here and cover the whole thing, right? Obviously, if there are four holes here, and trigonometry can only cover 3, 1 is not enough and 2 is too much, okay? So that's already the first problem here. So now I'm saying by taking away just one of them, it works. Now, you could verify what does it in particular mean. But I'm not going to even bother about that, but I want you to think about it. What it in particular means is, if this is true, if I cover the rest with trionimos, how many, each trionimal covers 3. So this whole thing covered by trionymies would have 3, it would be a multiple of 3. So it would be divisible by 3. So what I'm saying is that if you take any of these numbers and subtract 1 from it, then it is divisible by 3. That you might ask, is this true or not? That is something you can even verify. But that is not enough, right? Here is something that is divisible by 3, but you cannot, here is a board, let's say. Suppose we are in a board of this type that has 3 pieces. So a trionymy has 3 pieces, but there's no way that you can fill this up with a trionymal, right? Because it has the wrong shape. Of course, that is too easy to see, but it is not clear. Now, let's look at a different shape. Let's look at this shape here. Sorry. Let's look at a 3x3. Now that is 9, so that is a multiple of 3. So can we cover this? well, let's say we could put one here, we could put one here, but then we have this long piece here. And okay, we can try other ways, but you will see it always will run into a problem. That is a different problem. This is not induction. But I'm just wanted to show you that it is not obvious that this can be done, even if you know that the number matches. This is, the 3 by 3 has 9 holes, so 3 trinomials. If it can be covered by trinomials, it should be 3 of them, right? Because 3 times 3 is 9. But however I try, it won't work. Okay, I can try another one. Let's see what I can do. One more. I should do it in blue that you see a bit. I could say, okay, I tried this one here. Let's try this one there, but then this one here, and then it doesn't even connect. Try as you may, it won't work. So this is what I'm saying. Exploring here. Remember what I said. I want to understand a little bit. Understanding, or perhaps a better word is exploring the problem. You see that this is a rather subtle problem, because it is not true for arbitrary boards of the right amount, but it is true of these checkerboards. And now comes the proof, and the proof is so beautiful by induction. So proof by induction. Okay, proof by induction. The base step. So this is the statement Pn. I didn't write out the statement, I said it in words, but I'll say it again. If you have a 2 by n, 2n by 2n board, where in which one piece is covered, one square is covered, it could be a corner, it could be anywhere, right? I'm just saying randomly cover one of them, then the rest can be covered with trinomals. That's the statement, okay. And this is, we need at least a board of this size here. 2 by 2 board, or 3 by 3, 2 by 2 or 4 by 4, 8 by 8, 16 by 16. Remember, this has to be powers of 2. 3 by 3, for instance, doesn't work. So it is a bit more, the sizes are depending, the way that the size depends on n is exponential. Okay, so let's start with this board. So the basic step is P1, and that means that we are dealing with a 2 by 2 board, right? If n is 1, this is 2 by 2, this board. And now one of these things is covered by one, I randomly chose this one, but it is almost immediately trivial that the complement is actually a trinomial, right? If you put this, you see here, this is exactly, if you put the extra covered part here, or here, or here, or here, you get exactly the 4 possibilities, and each time you get exactly a trinomial. So it is very trivial to do this for a 2 by 2 board. But 4 by 4 board is already a little bit trickier. Also because there are many more positions that this blocked. It could be blocked. This one could be covered, this one could be covered, this one, this one, this one. There are 16 possibilities. Are we going to check all 16? Okay, so here's now the induction step. So again, assume Pn, so that is a 2n times 2n board. And then to show Pn plus 1, that is a 2n plus 1 times 2n plus 1 board. I'll just write down this number because that's the number that changes in this whole thing, right? N becomes n plus 1. Okay. All right, so let's highlight this. Oh, I have to do this bigger again. Sorry. This is what we assume. This is what we show. So therefore, we should consider this here. Give myself a little bit of space here. I'm erasing some parts that might be confused. So okay, no, that's fine. Let's leave it like that. So these are trinomials. We know how they look like, right? I just want to make this a little bit less. Okay, here's a board. Now, which board are we looking at? Well, I'm trying to show this. So I'm assuming this is a 2n plus 1, 2n plus 1 board. So there are 2n plus 1 here and 2n plus 1 there. Of course, I drew some number. It's obviously not the power of 2, but we have to imagine that this is 2n plus 1. Okay, this is the problem of drawing something with general n. You cannot do that, right? You don't know what n is. How can you draw it? So we draw something and we say, pretend that this is 2n plus 1. Okay. And now comes what I think one of the most clever ideas I've seen with this kind of thing, very clever idea, is let's split each side in half. So let's say this is the half here and this is half there. Okay, let's do that. Okay, so I'll do it in red perhaps. I'll do it here. So this is one and here. So what do we get? What is the size of this guy? Well, if I put this is half of that is 2n, right? And what is the size of this side? Also 2n. And this is 2n, and this is 2n. All these sides have now 2n. In other words, I have now 4 2n times 2n boards. The red boards there are 4 of them of size 2n plus 2. Now, since one is in the original one is covered, 3 of those are completely open, and one has one tile covered. Okay, and this is now the beautiful argument. Take the 3 that are not covered. So these 3, in this case, these are these 3. It could be any combination, but you can see it's if you turn this page around, then you get all possibilities. So it doesn't really matter in which corner I put it. Okay, and now comes the beautiful thing. Do the following coloring. Put one trinomial, one single trinomial I'm going to put it here. Okay, so how can I describe these? These are exactly the corner pieces, right? For each of these boards, I take all the boards that don't have anything, I pick each of these corner pieces. Together, there's a trinomial. Okay? So far, I have not really used the red boards now, but now I'm going to use my induction hypothesis. Now I'm thinking this of, green, this is something I know, 2n boards. By putting in this single trinomial, what is the result of that? That in each of these 3 boards, exactly one tile is covered now. But then, if one of the tiles is covered, I have to cover one. If I don't cover it, it cannot be done. We have seen this already, even by a 2x2. But once I cover one, so that's the reason on this tile, on this board here. This is a 2n by 2n board with one covered. By the induction hypothesis, it can be covered. So the induction hypothesis says that this can be covered. I repeat, why? Because it's a 2n by 2n board with one tile covered, namely the corner part. But that's also true for this one, and it's also true for this one, and it's also true for this one, because this is also one 2n by 2n board with one covered. In the 3 first cases, it is a corner piece. In this case, it might be any piece. Now, there was no restriction on where the piece, tile. It was no restriction on which tile we were covering. It's just the fact that one of the tiles was covered. Okay, that's what's happening here. So now let's think about this. If I have covered this, with trinomals, and this with trinomals, and this with trinomals, and this with trinomals, I'm done, right? This is the one single piece that is not being covered, and here I have this this is a trinomial. So these are a lot of trinomals. Together with this is a tiling of this checkboard, 2n plus 1 times 2n plus 1 chessboard, with this guy covered. And that's the solution. And it's actually interesting here. I mean, there are homework problems, but I'm not going to assign them, but I should look at it. So I would say here, do this now, even for a 4x4. So homework problem, but I'll put it between quotes. I'm not going to check it. It's just for your own benefit. Take a 4x4. Yeah? And suppose that this guy is covered. So find now a covering of by trinomals. Well, let's. I'm going to work this out here. So this is the 4x4, but the actual homework, let's do the 8x. I leave that for you, the 8x8. Okay, but I'll do the 4x4. Let's follow the argument here. Well, perhaps just, sorry, to not bias you against a particular quarter. Let's say this one is covered. Sorry, this is a bit too big. Let's make it red and also a little bit smaller here. Let's say this is the tile that is covered, and now the rest has to be covered by trianomers. Let's follow the procedure of the proof. The proof says divide in half, put a one trianomer piece in the corner like that. Sorry, I want to do this in blue. This is the one trianomer piece that we're going to fill in here. Remember, this is the first step in the proof. Okay. Okay, here this was green and now I made it red. I should have, perhaps red is a better color here, right? This perhaps is red as being, okay, fine. Okay, and now what we are left were, each of these are a 4x4, but we have seen how 4x4s are. They're very simple. This is just the complement, right? We just have one trianomer left. Here's a trianomer, here is one, here is one, and here is one. And here is the solution. You see the solution, right? Should perhaps, okay, let's not do the coloring here then. Here's the covering by trianomers. Notice that even if I would not carry out, if I would just give it to you like this, right, the original question, and I would ask you to fill this up, you might have to try a couple of times before you're able to find the right solution, right? You might say, okay, I'm going to put a piece here, but then you see that it doesn't work, and so on. But this gives you right away the solution. So now do the same for an 8x8. Pick a random tile, square, in that 8x8. And if you want to challenge yourself, take a corner piece, or take one on the side, or take one in the middle. Take something, and then solve it. And you'll see that what it involves is, if you do an 8x8, you cut it in 4 pieces, you get 4 4x4s, but then you have to solve the 4x4s using, again, this kind of argument. So you see, it's a nice exercise to see how induction works actually, what the type of things you have to do. And if you unravel the induction, you can solve the problem. Trust me, if you don't do the induction step and unravel it, it's going to take you a long, long time to cover generally an 8x8. It is not a simple problem. It's not something that you see by, of course, the 4x4, the 2x2 we saw right away. The 4x4 takes a little while. The 8x8, just trial and error, could take forever, but we have a method, and it's in fact a very effective method, but that is something for discrete math too. Okay, this is all I want to say about induction. I hope you saw how it can work in other cases than just by simple proving formulas, but on the final, I will only ask you to prove one of those formulas, the things that we did in the first lecture and also the homeworks of that first lecture. All right, there will be no homeworks for this one.